This project implements and compares several machine learning algorithms on multiple datasets and then re-implements key algorithm from scratch on the MNIST handwritten digit dataset. In the first part, the notebook uses 6 algorithms: K nearest neighbors, decision tree, multi-layer perceptron neural network, support vector machine, logistic regression, and K-means clustering. In the library import, in this cell, the notebook imports essential libraries such as pandas, numpy, scikit-learn modules, and plotting libraries. These import provides tool for loading data, pre-processing, training models, and computing metrics and visualization results. In the loading dataset, the notebook loads 3 datasets: wholesale customer, Horton Hospital, and the Bongabdo metadata dataset. Each dataset represents different real-world problems, so using multiple datasets help test how consistency each algorithm performs across different distribution. In the data preparation, the notebook cleans and format each dataset. Typical steps include selecting relevant features, handling missing values, encoding categorical variables if needed, and separating features from labels so that models can be trained correctly. In the fourth, each dataset is splitted into training and test sets using a function like train test split. The training set is used to fit the model and the test set is held back to evaluate performance on the unseen data, which is crucial for measuring generalization. In the algorithm implementation, we create and train one model of each algorithm, type on each dataset. The code typically defines a model object, fit it on the training data, and then stores predictions and probabilities that will later to be used to compute matrices and build a comparison table. In the evaluation matrix, a helper function calculates matrices such as accuracy, precision, recall, F1 score, and possibly AUC using the true labels and predicted outputs. Using a single function to compute matrices ensures that every algorithm is evaluated in a consistent and fair way across all datasets. The note in the comprehensive result table, all results are displayed into pandas.dataframe, creating a comprehensive table of algorithm, dataset, and their performance scores. It also identifies the best performing combination, for example, by highlighting the algorithm and dataset with the highest accuracy and printing this information clearly. In the visualization section, after computing matrices, we visualize performance using a bar chart for accuracy and F1 score across the algorithm and dataset. These plots make it easier to quickly see which model performs best and how the ranking of algorithm might change from one dataset to another. In the clustering evaluation, we run k-means on the feature space and evaluate clusters using metrics like Silhouette score. This shows how well the data naturally groups into clusters without using labels and allows comparison between supervised classification performance and unsupervised structure. In the confusion matrix, metrics are generated for the best performance of models on each dataset. These matrices show how many instances of each true class are correctly or incorrectly predicted, highlighting specific patterns of error rather than just overall accuracy. In the part 2, I have focused on MNIST classification without scikit-learn. In the first section, in the essential libraries, I import core Python and math utilities such as collection and NumPy plus Keras helpers to load the MNIST datasets. MNIST images are loaded as 28 by 28 pixels array along with their digit label 0 to 9. In the data preparation, the 2D images are reshaped into 1D vectors and normalized, for example, by scaling pixel values to a common range. This steps converts raw image matrix into feature vector that the custom algorithm can process efficiently in vectorized operations. In the custom k nearest neighbor, we compute distance between input and all training examples and find the k closest neighbor and predict the majority class among them. This implementation makes explicit how KNN relies on a distance matrix and how the choice of k controls the trade-off between noise sensitivity and smoothing. In the next custom decision tree implemented using a node class and a recursive tree building function. At each node, the algorithm evaluates candidate split using a criterion such as entropy or information gain, then recurs until stopping conditions like maximum depth or pure leaves are reached. In the custom logistic regression class that uses gradient descent to optimize the model weight. For each batch, it calculates the predicted probabilities and loss function, gradients with respect to the weight, and then update the parameters step by step until convergence or a fixed number of iterations is reached. In the neural network, a simple multi-layer perceptron is coded with one or more hidden layers. Using ReLU activations in the hidden layer and softmocks at the output layer. The implementation performs forward propagation to compute output, then back propagation to compute gradient. And update weights and biases for each layer. In the matrix evaluation, we use evaluation function which compute metrics such as accuracy for each custom algorithm on MNIST dataset. A central training loop trains each model, in turn record its performance and build a result list that is later converted into data frame for easy viewing. In the final comparison table, we displayed performance of KNN, decision tree, logistic regression, and MLP. It shows sample predictions, and this one shows the sample predictions made on the dataset, and this one shows the confusion matrix for the dataset. Thank you so much.